Okay, Algebra 2, we're back again. We've got some more solving to do. We looked at Descartes' rules of signs, kind of told us how many positive, negative, real roots to look for. We've used the fundamental theorem of algebra, which tells us how many total roots we can expect to find. We just got done looking at the upper bound and the lower bound, so we can find out what range of values that we actually have to look for. If you remember, we also looked at a remainder theorem and a factor theorem. Those are going to come into play today as well. So let's get started here because we've got a lot to cover in a short amount of time. Okay, so just a reminder, fundamental theorem of algebra, highest degree is the number of roots we have. Descartes' rules of signs, count the number of sign changes of the original function. You've got the number of possible positive real roots. Count the sign changes of the p of negative x, and you have the number of negative roots to look for, minus the 2's. Lowest integral upper bound and the greatest integral lower bound. They kind of separated those things off. Okay, so now today we have what's called the rational root theorem, and it states that p over q is a root, or you can call it a zero, of f of x if and only if f of p divided by q equals 0 and p is a factor of the constant term and q is a factor of the leading term. So p is a factor of the constant term. That's the number that's doesn't have a variable with it. And q is a factor of the original highest degree term, that number in front. So let's see how this works. Let's try one here. Find all the possible rational roots of 4x cubed minus 12x squared minus x plus 3. So our p has to be factors of 3. What are factors of 3? Well, it could be 3 or it's 1. Those are all the factors. Q has to be the factors of our leading coefficient. That would be the 4. So that could be a 1, a 2, or a 4. So now all the possible rational roots are all the p over q's that we can make. So that could be a 1 over a 1, or positive or negative, we don't know which one it is, and a positive or negative 3 over 1, and a positive and negative 1 over 2, and a positive and negative 3 over 2, and a positive and negative 1 over 4, and a positive negative 3 over 4. So I take all the factors of the last number, the constant term, which are just 3 and 1s, and I put them over all the factors of the leading coefficient, that 4. I'll let them all out here. So I got 1, 3, half, 1 1/2, 1/4, 3/4. Those are all the possible rational roots. So those are all the possible numbers I could try real easily without having to worry about a repeating or a non-repeating decimal that goes on forever, that type of stuff. So now you might get a problem that looks like this. Find all the rational roots, not just the possible ones, but the ones that actually work. So to do this, what we have to do first is we want to find all the possible rational roots, and then we want to do a quick Descartes rules of signs check. And then we want to find the upper and lower bounds on this. And then we want to use the remainder and factor theorems on only those numbers that work in that bound area. Okay, so we've already found all of our possible rational roots. We know there are 1, positive negative 1, positive negative 3, positive and negative half, positive and negative 3 halves, positive and negative 1/4, and positive or negative 3/4. So those are all our possible rational roots. Those are the only numbers we need to check with to see if this is going to work. So then the next thing, rule of signs change. Well, I got a 4x cubed, so for the positive real roots, I've got a 4x cubed to a negative, so there's one sign change, and then a negative to a negative, that's not a sign, negative to a positive. So I have 2 or 0 positive real roots. Okay, negative real roots, I got to find f of negative x, which would be a negative 4x cubed minus a 12x squared plus an x plus a 3, which says I only have one sign change. So I have one negative real root. So one of these possible negative numbers here is what I'm looking for. And then that leaves us with imaginaries as possibles. And we're only looking at imaginary right now just because that we have an idea what's going on. Well, 2 and 1 gives us 3, which accounts for all 3 of the total. And 1 and 0 gives us 1, which means there could be 0 or 2 imaginary roots for this particular guy. Okay, so those are all the quick finds there. We know how many roots we have to look for. We have all our possible roots. Now let's see, what's the highest value we can go with? So I'm going to set up my LUB, my lower bound. So I got a 4, a -12, a -1, and a 3. And if I run a 1 in there, I drop the 4. That'd get me a -8. -8 and -1 is a -9. -9 and 3 is a 6. Not all positive, so let's try a 2. So the 4 comes down, we get an 8, we get a -4, we get a -8, we get a -9 again. Then we get a -18, so we get a -15. That's not looking good. 3 gives us 4. 12, that would give us a 0. That would get us a -1. That would get us a 0. Not all positive, so we got to try 4. 4, that would get us 16. That would get us a 4. That would get us 16. That would get us a 15. That was 63. Okay, so 4 is our LUB. We don't have to look at any numbers greater than 4. So that's our greatest integer upper bound. So now let's look at the lower bound one. Again, 4, -12, -1, and 3. We did the -1, so it'd be 4, -4, -16, +16. -1 would be a 15, -15, -12. So that works out great in that -1 is our lower bound. So I don't have to try any numbers outside of -1 and 4. So when I look at my possible list of numbers here, I have to do positive and -1. I don't have to do -3. I don't have to do -1/2. But I do have to do all the rest of them. Here, let me see if I can just capture that. Oh, good. I can just clone that. Copy that. Let's bring that down. Okay, paste that in here. I don't need the +3. I don't need the +1/2. Oh, I don't need the -1/2. So I have all of these values to try. So now all I do is I plug them into the function and see which one. Is that what I want? Okay, so those are all my possible roots. Now, as a reminder, the remainder theorem says, remainder and factor theorem, if f of c equals 0, then c is a 0 or a root or a solution of f of x. In other words, there's no remainder, so that's what I have. So that would have to be a factor of that function. So I just need to try it on all of these numbers. So what was my equation? So f of 1 gets me 4 times 1 cubed minus 12 times 1 squared minus 1 plus 3. And if I run that through, I get -6. Okay. F of -1 would give me 4 times -1 cubed minus 12 times -1 squared minus the -1 plus 3. If I run that through, I get a -12. Okay, so f of 3 was our next number. F of 3 is 4 times 3 cubed minus 12 times 3 squared minus 3 plus 3. And if I run that through, I get 0. Hey, there's one of our solutions that we're looking for. Okay, so that tells me, since I had 2 or 0 positive real roots, I have another positive real root and I have a negative root yet. So it might be one of these rational numbers. We don't know, but it may not be. So I'm going to try a 1/2, because that's just the next number in my line. So I got 4 times 1/2 cubed minus 12 times 1/2 minus 1/2 plus 3. And if I run that through my calculator, I get 0. There's my second one. I have both of my positive real roots. Now I just have to find a negative real root, and I want to just go with the next number here, -1/2. See what happens. So I got 4 times -1/2 cubed minus 12 times -1/2. That was supposed to be squared. Minus a -1/2 plus, and I get 0. I found all 3 of them. So 3, 1/2, and -1/2 are the actual rational roots of our function 4x cubed minus 12x squared minus x plus 3. These are the 3 numbers that actually make it equal to 0. Now here's a little thing to point out to you. when we did our greater and lower upper bounds, we should have already noticed that, hey, we had a remainder of 0 when we did the 3. So we already knew one of them. We should have used that to our advantage. Now, the next part of the assignment is going to say find all of the zeros. Now, how is that different from what we just did? Because what we just did is we found the rational ones. This says find all of the zeros. So once again, we want to go through that whole process that we did the last time. What are the possible roots? All the factors of 3 are 1 or 3. All the possible factors of 6 are 1, 2, 3, and 6. So all of our P over Qs are positive negative 1, positive negative 3, positive negative 1/2, positive negative 3/2, positive negative 1/3, positive negative 3/3, positive negative 1/6, positive negative 3/6. So those are all our possible rational roots. Now, keep an eye out for repeats. We don't want to put repeats down because they just waste time. 3 over 3 is 1. That's a repeat. We don't need it again. 3 over 6 is the same as a half. We don't need to put it down again. So our possible rational roots are positive negative 1, positive negative 3, positive negative half, positive negative 3/2, positive negative 1/3, and positive negative 1/6. Those are the numbers that we have to use. Okay? Then our next step was to do the how many positive real roots are we looking for? How many negative real roots? And how many imaginary? Now, notice it said all zeros. So that means this time we might have to find imaginary roots. So let's check. Positive real roots, I'm looking for sign change. I got a positive 6, negative 17, that's 1. Negative 17 to positive 8, that's 2. And then I got the 8x to a negative 3, so that's 3. Or down by an even number, or 1. So I definitely have a positive real root. Okay, so now m of negative x, if we run it, the 6x to the 4th stays that way, but now the 17 will go to a positive. The 8x squared would stay positive, but the 8x would go negative. So we have one sign change, so there's one negative real root. 3 and 1 account for 4. There's 4 total roots, so that means there's 0 imaginary, or I got 1 and 1, and 4 minus 1 minus 1 will give me 2. So either I have 3 real positive zeros or 1 negative real 0, or I've got 1 positive, 1 negative, and 2 imaginaries. Okay, so now next step, we check our LUB and our greatest lower bound. So our upper bound and our lower bound. So 6, negative 17, 8, 8, and negative 3. 6, negative 17, 8, 8, negative 3. Get those down there. Okay, so if I do the 1, I get a 6. I get a negative 11. I really could stop right there because that says I don't have all positives. But I'm going to go ahead and run through it anyway, and then we would get negative 3, and then a 5, and then a 2. Okay, so then if I do the 2, I get a 6. I'd be 12. Negative 17 plus 12 is a negative 5. Again, I could stop because I already got a positive negative. It's not going to work. We're going to go ahead. Then I would get a, negative 5 times 2 is a negative 10 plus 8 would be a negative 2. And that would give me a positive 4. That would be 8. That would give me a 5. Okay, one last. Let's try again. 6 times 3 is 18 plus 11. That gives me a 1. 3 and 1 is 3 plus 8. That's 11. 33 plus 8 is 41. 41 times 3 minus 3 is 120. So we have our upper bound at 3. We don't have to pick any numbers over 3. That's good. Okay, so let's do the lower bound. If we do negative 1, 6, negative 6, negative 23, positive 23, 31, negative 31, negative 23, 23, 20, and we have our lower bound. Now, I'm going to tell you right now, it is not always negative 1 on the lower bound, although it seems like that with what we have. Okay, now, what do we have to do? We have to check all of our possible rational roots between 3 and negative 1. So I can eliminate some more of these. I don't need the negative 3 to check. I don't need the negative 1.5 to check. I do have to run all the others. Now, at this time, what I would do is I'd probably use a spreadsheet or something to do the math a lot faster, unless you just want to plug stuff into your hands. Sorry for that. I'm switching sides of the computer here. Okay, so I'm going to bring up a Excel document. You can also do this on Google Docs or whatever. It doesn't matter what you use. So the first thing you do is you got to take and plug in all of those numbers. Okay, so what were all of those numbers? We had 1 and negative 1 and 3 and a positive 1/2 and a negative 1/2 and a positive 3 divided by 2 and a positive 1 divided by 3 and negative 1 divided by 3. Notice when I'm putting in the 1/3, even though it's a positive, I'm still going to hit that positive so I get it. So positive 1 divided by 6 and a negative 1 divided by 6. Okay, so now that I got it plugged in there, I'm just going to, in B, I'm just going to plug in a formula, and it's going to say equals 6 times, well, I want that A1 cell raised to the 4th power minus 17 times that A1 cell raised to the 3rd power plus 8 times that A1 cell raised to the 2nd power plus 8 times that A1 cell minus 3, and I get a 2. And now all I'm going to do is I'm just going to drag that formula all the way down, and I'm looking for zeros. So as I do this, I notice that the 1 is a 2, and the negative 1 gets me a 20, and the 3 gets me a 120, and the half gets me 1.25, and the negative 0.5 gets me a negative 2.5. But notice the 1.5, which was 3 over 2, got me a 0, and the 1 over 3 got me a 0. So we have 2 solutions here, and then the rest are negative numbers. So we have 2 solutions. So we have x equals 3/2 and x equals 1/3 as our 2 of our 4 zeros. Okay, back out here. So of all of our roots, don't save it. I've got lots of stuff going on here. Just close this stuff. Let me just click here. There we go. Okay, so we have x equals 3/2 and we have x equals 1/3 as our 2 of our 4 solutions. Well, this means 2x has to equal 3 and 3x has to equal 1. And if I go to that next step, that would say 2x minus 3 would have to equal 0 and 3x minus 1 would have to equal 0. So those are 2 of our factors. So now what do we have to do? We have to take our whole 6x to the 4th minus 17x cubed plus 8x squared plus 8x minus 3 and divide it by, what do we have? 2x minus 3 by the 2x minus 3 and by the 3x minus 1. So I've got to take that whole thing, divide it by the 3x minus 1, get an answer, take that answer, divide that whole thing by 2x minus 3. Now, if these would have been nice whole numbers, I would have done it by synthetic division. But since they're not whole numbers, I've got to use long division. So I went ahead and did the long division ahead of time. And when I took the 6x to the 4th minus 17x cubed, move that to right there, plus the 8x squared plus the 8x minus 3, and I divided it up by the 3x minus 1, I ended up with 2x cubed minus 5x squared plus x plus 3. So then I took that 2x cubed minus 5x squared plus x plus 3, and I did long division on 2x minus, divided that by 2x minus 3, doing long division, and that got me to x squared minus x minus 1. So that meant that 3x minus 1 times 2x minus 3 times x squared minus x minus 1, all those multiplied together had to give me the 0, because that's what I was looking for. Which means that each one of those would have to equal 0. So the 3x minus 1 would have to equal 0, the 2x minus 3 had to equal 0, and the x squared minus x minus 1 had to equal 0. Well, the 2x minus 3 equals 0 was already one that we had. It was the 2/3, and the 3 halves, and the 3x minus 1 equals 0 was our other one, which was our 1/3. So that just means I got to use quadratic formula on the last one, and I get 1 plus or minus the square root of 5, all divided by 2. Okay, so what does this mean? This means I was able to find the roots using this rational root theorem. Back up at the very top of our note page, so to speak. So I try to find all the possible rational roots by looking at the factors of the last number and putting them over the factors of the first number, and then I plug them into the equation to see which one gets me a 0. Whichever one gets me the 0 is the rational root. Okay, there's that part. I think you're ready to go now.